Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, welcome back. This is part 2 of our lesson number 5 of Calculus 3. And this lesson talks about comparison test and limit comparison test. Okay, so for our first theorem, says here you are given series a sub n and b sub n, and then here the terms of the series satisfies this inequality. B sub n is bigger. The terms of the series is bigger than a sub n for all n. Remember, this is for all n. If the terms here, if this series is convergent, b sub n, then the smaller one, a sub n, is convergent. So this is theorem 1 in comparison test. Okay, so as you can see here, this one. Okay, if this is let's say larger, okay, based on this one, okay, based on this inequality, then the smaller one, this one, a sub n, is convergent. So however, if for the second theorem, for the comparison test, this one, let's try another, let's say color green, this one. Okay, that one. If this is smaller, okay, smaller one, okay, so as you can see here, if this smaller is divergent, then the bigger is also, the larger is also divergent. So that's how you are going to use the comparison test or direct comparison test. Okay, so all you have to do is to satisfy this what they call this inequality. Okay, it must be a, what they call this one, it must be a positive term series for all n. Okay, so that's how you are going to use the comparison test. Okay, so let's have an example here. Let's move down. Okay, let's move down. Let's have an example here, illustration, where can we move upward? Okay, this one here. Let's have an example. Let's say color black. Example here. Example. Okay, using use comparison test. Comparison test. Okay, so example number 1. This series of 1 over 4 to the n plus 5, where n starts from 1 to positive infinity. Okay, so as you can see here, as I've said in the introduction, that there are given or problems that are that resembles a known series like p series, geometric series, or let's say it's a known series, and then it resembles, but then you cannot use the theorem for the known series All you have to do is to test the series using comparison test if that series is convergent or not. Okay, so anyway, uh, this example here, as you can see, this resembles, okay, resembles a geometric series, a geometric series. Okay, so this is our a sub n. As you can see here, is this our a sub n or b sub n? So that's a nice question, but actually this is our b sub b sub n. Okay, this is our b sub n. Why? As you can see here in the theorem, uh no theorem, uh yes, okay, if what they call this one, it should be that the bigger, what is, okay, the smaller, okay, which one is bigger? Let's say the bigger must be, okay, this must be our b7. Why? Because if this is, no, this must be a sub n. Okay, this must be a sub n. Let's go back. Okay, a sub n, because this will become smaller later. Okay, it just and the we compare this series, the given series, to a known series. So the known series is a geometric series. Okay, except that we have to, what we call this one, we have to eliminate this term here, plus 5. Okay, so what we will do here is the series, we will compare, what happened, okay, we will compare the series, we will compare the given series to uh, this series here. Okay, okay, our given series is this one. Okay, this is our given series, but we will compare to this one, summation of 1 over 4 to the n, where n starts from 1 to positive infinity. So it starts with, as you can see, with 1. So therefore you have to start also the given series, the one that you compare to, the index must start with 1. Okay, so what happened, okay, it's not moving. And now this is our what they call this one, b sub n. Okay, this is our b sub n. I'm confused before whether I will choose the notation for the no the given series as b sub n uh, or a sub n, but when I analyze it, it should be the given must be a sub n. Term by term comparison, as you can see, term, let's go back, as you can see here, what happened. Again, let's wait for the program to respond. What happened here is that, okay, term by term comparison. Okay, term by term, term by term comparison yields, notice that before this you have to recall our previous discussion. If a and b are positive real numbers, then and also and also what happened, and a is less than b, or maybe equal, it could be, then 1 over a is greater than 1 over b. Okay, this remember this one. Okay, let's remember this one. Okay, notice that it's very clear that 4 to the n is less than, or this is equal to 4 to the n. Okay, however, if you add, okay, if you add 5 here, okay, if you add 5 the right hand side, this is greater, okay, for all n greater than or equal to 1. Okay, but to make it safe, let's use equal. Okay, it doesn't matter. Okay, so from here, this is our this is our a, okay, and this is our b. Okay, so can I move this up, or sorry, can I choose another color? This is our a, okay, and this is our b. By using this theorem, this recall, we can write this as 1 over this is our 1 over 4 to the n, which is bigger, 1 over 4 to the n greater than or equal 1 over 4 to the n plus 5. Okay, for all n greater than 1. okay, using this recall. So as you can see, this is our, let's try another color. Let's say, can we have color green? Okay, this one. Can I choose the green color? Do we have an internet connection? Okay, sorry. Request timeout. This one. Okay, this is our B sub M. Okay, and this is our A sub M. So as you can see, this is the known series. One summation of 1 over 4 to the n. N starts from 1 to positive infinity. This is a geometric series. Okay, and we know that in a geometric series, the sum is equal to a over 1 minus r, as long as your r is between negative 1 to 1. Okay, so let's try. And based on the, as you can see here, as you can see in the assumption that B sub n or B sub n must be convergent in order to use the comparison test, uh, 1, this one, theorem 1 in the comparison test. So this must be larger. Okay, so we choose a series which is larger than what they call this one, larger than the given. Okay, can you use another, let's say 1 over 2 to the n? Yes, of course, you can use, as long as there's a, you can compare the terms of the series, uh, and you show that it is less than or equal this one. Okay, as long as you can use that. Okay, so from here, this is a geometric series. We can write this as summation of 1 over 4 times 4 to the n minus 1, n starts from 1 to positive infinity. So from here we have 1/4 1/4 times 1/4 n to the minus 1, n starts from 1 to positive infinity. Okay, so clearly this is a geometric series where r is 1/4, which is of course between negative 1 and 1. So our a is 1/4, 1 minus 1/4. So this is 1/4 multiplication 3/4, 3/4, 3/4. 1 minus 1/4 is 3/4, reciprocal 4 over 3. So cancel, so we have 1/3. So the sum of this geometric series is 1/3. Okay, this is convergent. So by comparison test, we show that this is true. So our conclusion, can we write our conclusion here? This is conclusion. Therefore, okay, therefore the series series summation of 1 over 4 to the n plus 5, n starts from 1 to positive infinity, is convergent by comparison test. Comparison test. Okay, so please don't forget to write the conclusion. So let's recall, all you have to do is to find a series that you are going to compare, and then after finding that series, make sure that it satisfies the theorem of the what they call this one, the this one, this theorem. Make sure that it satisfies this condition. Okay, and then if the, it says here, if the bigger series is convergent, then the smaller is convergent. However, if you use theorem 2, if the smaller series is divergent, then the bigger series or the larger series is divergent. Okay, let's have an example for theorem 2. Let's have an example here. Example number 2. Okay, that's this one. This series, example this one, 1 over square root of n, where n starts from 1 to positive infinity. Okay, infinity plus, let's say, plus 7. Okay, so solution. What happened? Do we have an internet connection? There is. So solution. Again, we will compare the series to a known series. Okay, so let's try to compare the series to a what known series. Let's say this form is a, what they call this one, this form is a p series. Okay, so we will exclude the term plus 7. Okay, so we will compare the given series to the series summation of 1 over square root of n. N starts from 1 to positive infinity. Okay, this is a p series with p is equal to 1/2. Okay, so let's put a, you have an internet connection, request timeout. Okay, this is a p series or hyper harmonic series which is convergent. Okay, this is a p series with p which is equal to 1/2, which is divergent. Okay, can we have another, can we compare to other series? Of course you can, as long as again it satisfies the condition. So that's term by term comparison yields, as you can see, before choosing our an or bn, let's try to compute it first. Okay, we know that let's try this color, blue. We know that square root of n is equal to square root of n. But what if you add 7, which is bigger? Okay, of course, the bigger one is the right hand side. Okay, So square root of n is clearly greater than, to make it safe, we can use, oh, what happened? It's because of the internet connection. We know that this is true. To make it safe, we will put equal sign. Okay, for all n greater than or equal to 1. Okay, so what happened here? Based on our uh, discussion before, that 1 over square root of n is greater than 1 over square root of n plus 7. Okay, for all n, based on our recall. Okay, so as you can see here, uh, as you can see, this is our this one, this is our bn. Okay, this is our bn, and this is our an. Okay, so from the previous, this is divergent. So if the larger is divergent, the smaller is divergent. Okay, if the larger is divergent, the smaller is divergent. If the larger is convergent, the smaller is convergent. Okay, that's basically what the theorem says. So as you can see here, this is divergent. Okay, so what's our conclusion? Let's move it somewhere. What's our conclusion? Can we move this to, okay, this one. So our conclusion, therefore the series summation of 1 over square root of n plus 7 n starts from 1 to positive infinity is divergent by comparison test. Okay, so that's how you are going to use the comparison test, or some other books, as I've said, it's what do you call this one? It's direct comparison test. Okay, so again, if the bigger, this one, if the bigger is or the larger is convergent, the smaller is convergent. If the larger is divergent, then the smaller is divergent. Okay, that's for the comparison test. Okay, so all you have to do is to satisfy this condition. Okay, so for our next theorem, which is which talk about the limit comparison test, which will come shortly. Okay, so I hope I hope that you able to comprehend how to use the uh, direct comparison test. Okay, so just wait, or maybe do you want some um, more examples? Okay, let's decide on that maybe after this. Hello everyone, let's go to example number 3. I've decided that I have to add more, maybe 3 more examples. Okay, so let's have example number 3. We have summation, no, uh, this one. Does the following series converge? Okay, we have 7 plus 1 third plus 5 minus 2 plus 1 over 2 factorial plus 1 over 3 factorial, 1 over 4 factorial, plus and so on up to 1 over n factorial. Okay, so using the, what they call this one, using the direct comparison or comparison test. Okay, so remember that these terms here, these terms here resembles the previous what they call the example. This is summation of 1 over n factorial, where n starts from 2 to positive infinity, and we know that in our this is convergent. Okay, convergent by previous example. Okay, previous example. Okay, and we compare this series to the geometric series 1 over 2 to the n. Okay, so remember that there are other terms here. This one, there are 4 terms, okay, that were added to this series. So in our previous lesson, we discussed that we can actually eliminate these terms here, finitely many terms. All you have to do is to consider the tail of the series, meaning to say those that are approaching to positive infinity. Okay, there are more terms here in the positive infinity than these finitely many terms. Okay, so we can discard this one. So let's recall our previous discussion. Recall our previous discussion that the convergence or divergence of an infinite series is not affected. Okay, is not affected by discarding a, what they call this one, discarding a finite number of terms. Okay, discarding a finite number of terms. Okay, so meaning to say, if this series is convergent, if you add finitely many terms, finite number of terms, then the convergence or divergence of the series is not affected. Okay, by our previous discussion. Okay, so therefore the series, this one, let's denote this as uh, asterisk. Again, let's wait for the program to respond. We have an internet connection here. The series, this one, we denote this one as double asterisk. Okay, the series double asterisk is convergent. Okay, so that's how you are going to solve if you encounter that kind of situation. Let's have another example, number 4. Let's try to again, let's wait for the program. Let's say we have our an internet connection, we are connected. Okay, so let's try number 4. Okay, let's try color black. Okay, how about this series? Again, using what they call this one, using comparison test. E to the negative n squared, where n starts from 0 to positive infinity. Okay, so let's have a solution here. This series number 4, or for example number 4, is was given in our exam. So maybe you have an idea now that this series is convergent. Okay, this series is convergent. Maybe you can use I think I remember that this is in the integral test. Okay, so let's try to solve this. Recall that this is our what they call this one, this is our term, this is our an. Okay, so let's simplify first the an, a7, negative e to the negative n squared is equal to 1 over e to the n squared. Okay, this is basic algebra. So what will you do here is, again, you have to remember the recall that we discussed before. Let's try to find a known series which is convergent. Why convergent? Why I said that this is convergent? Because as we saw it in the exam, this is convergent using integral test. Okay, so let's try to prove this series, example number 4, is convergent using direct comparison test. Okay, so how? Okay, remember that note that note that what they call this one, e to the n, e to the n, and n, which is bigger, okay, which is bigger for all n greater than 1. So remember why we exclude 0. So you will find out that later. Okay, so for all n greater than 1, remember that e to the e is 2.71 approximately. So e to the 1 is 2.71. This is 1 on the right hand side. If n is 2, so we have 2 here, and then we have 2.71 raised to the power of 2. So this is much, the left hand side is much, is clearly bigger than or larger than the right hand side. So e to the n is clearly uh, greater than or equal to n, for all n greater than 1. Okay, we include the symbol equal here to make it safe. Okay, so what will happen if we raise uh, if we raise our n, the e to the n, if we raise to n, what will happen on both sides? Okay, is the expression on the left hand side still bigger than the right hand side for all n? And we know that it is clear that this is greater. Okay, this is clearly greater because as you can see, our n here is positive. Okay, positive integer, which is greater than or equal to 1. This is true. Okay, so simplify. This is e to the n times n. Okay, which is clearly greater than in our previous discussion. Okay, and for all n, what is the algebra behind this? Okay, what is the algebra behind this? Remember that in your algebra and trigonometry class, we know that a to the m raised to the power of n is equal to a to the m times n. Okay, so I know that you are very familiar with this one. So n times n, we have this one. Okay, but n times n, sorry, but n times n is n squared. Okay, n squared. Okay, and 3n for all n greater than 1. Okay, so however, this is also true. Okay, that you can show that this one, that this is also, that this term here is, and also here, is greater than n squared for all n greater than or equal to 1. Okay, so by transitivity, we have en squared is greater than or equal to n squared for all n greater than or equal to 1. Okay, so from this this is now our b sub n, and this is our a sub n. Okay, let's move to the other side. This implies that 1 over e to the n squared is less than or equal to 1 over n squared. Okay, so from now on, this is our b sub n and this is our a sub n. Okay, so this is our b sub n and this is our a sub n. Okay, and the series that we are going to compare to the given is this series. Okay, summation of 1 over n squared, summation of 1 over n squared, where n starts from 1 to positive infinity, and we know that this is a p series. Okay, this is a p series with p which is equal to 2, which is convergent. Okay, so therefore we have shown that since this is convergent and the series a sub n also uh, convergent, okay, based on the uh, what they call this one, on the theorem. Okay, so this implies that summation of 1 e to the negative n squared, or n starts from 0 to positive infinity, is less than or equal to summation of 1 over n squared, and n starts from 1 to positive infinity. Okay, so this implies again that the original series, okay, series is convergent. Okay, by the comparison test. Okay, so we have shown that the given series, the original series, is convergent. Okay, let's look at the graph. Okay, let's verify. Notice that our original series is 1 over e. Where is e here? Exponent miscellaneous. We have close open negative x squared close. Okay, this is our series, 1 over e to the x squared. Enter. And the series that we compare is the series 1 over x squared. 1 over x squared. No, this is one. This is this one. Okay, enter. Okay, so remember that our n starts at 1 here. Okay, so clearly when your this one, okay, n starts from 1 and our e starts from 0 here. Okay, so clearly the blue one, this is much what they call this one, this is much 1 over x squared is much bigger than 1 over e to the x squared. Okay, as you can see in the graph. Okay, even if you zoom out up to the end, suppose this one 12, you can see here in 12 that the almost the two series are overlapping each other. But if you zoom out, clearly the blue one, is this blue or violet? The purple one is much uh, bigger than the value of uh, 1 over x squared is much bigger than 1 over e to the x squared, and you have 12 here. Okay, this is the green one, and the green one is the original series, while the blue one is the series that you are going to compare. Okay, so as you can see here, uh, the series is convergent. Okay, so that's problem number 4. Do you want some more problem? Can we have some more problem? One more. Let's try number 5. Number 5. Let's try this problem. Okay, let's try summation of uh, let's say 4 to the n over 5 to the n. No, 3 to the n. Let's try 3 to the n. 3 to the n plus let's see, minus 1, where n starts from 1 to positive infinity. Okay, let's try to solve this. Remember that the term here resembles the geometric series. Okay, so this resembles, can we move it to, do we have an internet connection? Maybe I will delete this. What happened? Do we have an internet connection? Okay, we have. Why it takes so long to respond? Here. Okay, let's try. Okay, let's make a circle. Okay, anyway, this resembles the geometric series. Okay, as you can see here, we have, this is 4 over you can write this as 4 to the n over 3 to the n. Okay, let's try to eliminate this constant term. Okay, and then let's observe. Okay, that's basically one of the techniques on how to find the how to use the, what they call this one, the convergence test. And we know that this is 4/3 to the n, so we can write this as 4/3 times 4/3 to the n minus 1, and 4 over 3 is 4 over 3. The decimal value for 4 over 3 is let's say 4 divided by 3 is 1.33. Oh, what happened? Let's wait for the, maybe I have to erase this one. no, no. uh, let's delete this. Let's try 4/3. Let's try this is 1.333. Am I right? And this is our r. Okay, this is our r, but this is greater than or equal to 1. So this therefore this series is this symmetric series is divergent. Okay, this implies that uh, this series, if you put a summation, we have divergent. Okay, so anyway, uh, let's try to compare uh, this series to this one, which is bigger. Okay, so if you have this mass, okay, you can, let's try to delete this. Let's compare 4 to the x. Okay, 4 to the x divided by 3 to the x. 3 to the x. Okay, 3 to the x minus 1. Okay, so this is the graph of, clearly the series is divergent. Okay, compared to 4 to the x over divided by 3 to the x. 3 to the x. Okay, so what happened? Clearly the original series is much bigger than the series that we are going to compare. Okay, so this is our a sub n, but this is our b sub n. So if you look at the graph, if you move upward and you zoom out, the black one is clearly bigger. The value is greater than the red one. Okay, so we verified that clearly the series. Okay, so let's try to compare. Let's try let's try to compare our we what is the right what do you call this one, the right word that I am we will compare to the given we will compare the given series to. Okay, this one we will compare. Okay, we will compare to the given series or the original series. This is what we call the given series is the original series to this series, summation of 4 to the n over 3 to the n, where n starts from 1 to positive infinity. And this is our b sub n. Okay, our b sub n. So if you look at the graph, okay, this is our the black one is much bigger. The black one is much bigger than the red one. Okay, so this is our bn. Okay, this is our okay, let's forget that first. Okay, term by term what do you call that, term by term comparison yields this one how are we going to compare? Okay, so that's for okay yields. Sorry, I forgot to put my eyeglasses. Okay, yields. We know term by term comparison yields. We know that 3/4. Say this one. 3/4 is this equal 3/4 is equal to 3/4, right? If you raise that to the nth power, is just the same for all n greater than or equal to 1. Okay, that's clearly true. Then if you have to simplify, this is 3 to the n over 4 to the n. This is 3 to the n over 4 to the n. And again, this is also true. Okay, let's move here. So what will happen if we subtract the exponent by 1? Okay, so what is the inequality here? 3 to the n over 4 to the n for all n greater than or equal to 1. So is the left hand side greater than the right hand side? Okay, so let's try to analyze that using a graph. Okay, let's try 3 to the x. We use x here because the variable n is not permitted to the Dismos graphing online calculator. Let's move divided by 4 to the x. 4 to the x. Okay, this is the graph of 3 to the x over 4 to the x, this one. Okay, so let's try to graph the left hand side. Let's put a grouping symbol. -1 raised to the power, okay, divided by 4 raised to the power of x. Okay, so let's compare. So clearly the first graph, the green one, is much the value of this function is much bigger than the purple one. Okay, the 3 to the x minus 1 over 4 to the x. If you zoom in here, as you can see, it is number 13. As you can see, it's overlapping. So but if you zoom out, look at, okay, so can you see the green? Where's the green one? Okay, where's the green one? Can we change that to other color, like like orange or red? Okay, where's the, okay, let's try to go back. No, that's the reason why. As you can see here, okay, zoom out. Is it clear? Or maybe how about the number 6? Can we try to expand? Can we use this one? Okay, that one. Okay, the bread graph is, which is 3 to the x over 4 to the x, is much bigger value than the purple one. Okay, so this means that this question mark here, I will erase this, okay, and replace this as this one. Okay, that's greater for all. So therefore, if you take the reciprocal 1 over, this is take the reciprocal 3 to the n minus 1 over 4 to the n. Okay, the inequality symbol is reverse, 3 to the n over 4 to the n for all n greater than or equal to 1. And if you simplify this, you have 4 to the n over 3 to the n minus 1, which is greater than 1 over, no, 4 to the n over 3 to the n for all n greater than 1, greater than or equal to 1. Okay, so as you can see in the discussion, the this is the series that this is the original series on the left hand side, and it says that if the smaller series, the a sub n, okay, if the a sub n is divergent, okay, the a sub n is divergent, this one, okay, the a sub n is divergent, then the bigger series is also divergent. Okay, that's basically what's is saying in the limit in the direct comparison test or comparison test. Okay, so this implies that the uh, series, this one, uh, 1 over 4 to the n over 3 to the n minus 1 and starts from 1 to positive infinity. Okay, this one, this is 4 to the n over 3 to the n starts from 1 to positive infinity, and this series here is divergent. Okay, by our previous discussion before, if you look at here, this area here, let's wait again for the program to respond. Do we have an internet connection? We have. So what happened? So let's wait. This one is divergent. Okay, geometric series, okay, with a is equal to 4/3 and r, which is equal to 4/3. So okay, so that's what happened. Again, let's wait. This takes a lot of time. We have a connection. So as you can see, the series, this one, this is our b sub n. Okay, so this is our b sub n, and this is our a sub n. Okay, one. Let's move again. Let's put the conclusion. Therefore, the original series, this one, 4 to the n over 3 to the n minus 1, 1 to positive infinity, is divergent by comparison test. Okay, so we have 5 examples. I know that's enough, so I hope that you comprehend on how to use the comparison test. So just all you have to do is to compare, okay, based on the title or the name of that test. So let's go back to our theorem. You move upward. So what happened? This one. Okay. Says here, if the bigger series is convergent, then the smaller series is also convergent. That's theorem 1 of the comparison test. So for theorem 2 in the comparison test, it says that if the series is smaller is divergent, then the bigger series is also divergent. So that's basically what's the theorem 2 of the comparison test says. Okay, so for our part 3, we will be discussing about the limit comparison test. Okay, thank you so much for watching.